The first speaker tonight is John Hayes. He's the recipient of the Barry Jacobs Memorial Award for research in the psychophysics of human taste and smell. John received his BS and MS degrees at Brown University, where he worked with a well-known figure in our field, Harry Lawless. He then went to Yale for a few years and worked with Barry Green before moving to the University of Connecticut, where he got his PhD in nutritional sciences with Valerie Duffy. He then moved on to do a postdoc at the Center for Alcohol and Addiction Studies, also at Brown University, where he really widened his scope of expertise. And he's currently on the faculty at Pennsylvania State University in the Department of Food Sciences. In addition to all of his scientific achievements, some of which you'll hear about tonight, he's been very instrumental in communicating some of the advances in our field to the general public, having been interviewed by the media, it seems, at least 10 times over the last 2 years. And that's more times than I've ever been interviewed by the media in my life, so I think that's pretty cool. And tonight's, the topic of his talk tonight, or the title, is Using Psychophysics to Understand the Perception of Real Foods. John.
Thank you very much, and thank you for the kind introduction. I really need to just stop picking up my telephone when I don't recognize the number on caller ID, because on Monday, the New York Post called, and they wanted to know about Google Trend data that was showing that Bernie Sanders supporters were searching for recipes like authentic Mexican enchiladas, and Donald Trump supporters were searching for things like pork chops. And they wanted to know what that meant. So I patiently explained a third variable problem and explained that it was probably all just the demographics of those two groups. Of course, that didn't make it into the newspaper. So if you really want to know what the Post quoted me on, you're welcome to look at it this week. So I really think that the most interesting science happens at the interface of various different disciplines. And so that's why, as a food scientist, I'm inherently applied, I'm inherently translational. Food scientists have been applied and translational and multidisciplinary for decades. We just didn't know we were supposed to call it that to NIH. And so I often go to food meetings, and I spend my time at food meetings trying to explain basic neurobiology. And then I come here, and I'm probably the most applied person in the room. So then I sit here and try and explain food. So I thought for today's talk, I would actually go ahead and talk about food, since it's something that I'm very, very passionate about. So when you think about your body of work, when you get an award of what you're going to talk about, I went and I took every paper that I've ever published, and I fed all the titles into Wordle, and I made a word cloud. So this is every paper I've ever published, and so you can see, I've worked on TAS2Rs, genotype-phenotype associations, taste, perception. I also do some work on women's health. We do some HIV prevention work in my laboratory. I will not be talking about that tonight. I also do a lot of applied work. And I decided that I would actually go through and strip out all of the genetics from my entire talk. So there will be no genetics here tonight, I think maybe with one exception, because I know Steve's going to give you a great talk about genetics in about 35 minutes. So when you think about studying food as a perceptual scientist or as a behavioral scientist, historically within sensory evaluation, people were interested in studying the product. Trey Gengen wrote a great book chapter in the 1970s called Humans as Sensors. And it really talks about how, from an applied product perspective, which wasn't Trig's area, but from an applied product perspective, you could really use people, but you had to have good psychophysics to know how to calibrate those instruments. Just as I can't walk into the laboratory and use a bunch of uncalibrated pH meters, if I'm going to use humans as sensors, I have to understand how that system works. And I know for the graduate students in the audience, you always get really, really nervous when your PI tries to come back to the bench and you worry, do they even know how to use a pipetter anymore? Well, in my lab, sometimes we face a different problem. They don't let me interact with the people anymore, my students don't, but when we're really shorthanded, sometimes you can find me putting on my whites and going down and frying chicken. So here I am actually frying chicken the same day I had an RO1 due. So I'm sitting there checking my phone, trying to make sure that my grant went in while I'm getting absolutely covered in grease. I know far more about preparing chicken sous vide than you ever wanted, because sometimes we want to do something like a triangle test with chicken. So this is Rosemary Pangborn, and older scientists in the room may or may not remember Rosemary. I would imagine that most of the younger scientists in the room have never even heard of her. Rosemary, among the applied food sensory people, she is the matriarch of the field. She literally defined the field in North America. She was at UC Davis for many decades, wrote a definitive textbook in the field, trained most of the graduate students that went on to head most of the sensory research groups at most major food companies in North America. And she was active in the chemical senses when she originally started out because it was a very small community. In fact, here's a photograph of her, not from a food meeting, but from the second ISOT meeting in Tokyo. And also, older members will remember that I went back to the AChemS archives. Google's a great thing, and you can find this online. And what you'll actually see is that Rosemary Pangborn was actually the membership committee chair, and then she was also, over here in the corner, she was actually the secretary for the first 4 years of AChemS existence. So how many of you in the room actually attended those meetings and remember Rosemary? All right. So not only as the secretary, she actually produced the very first AChemS newsletter. And I thought this was really funny because she said it was great to communicate with everybody that nobody actually submitted anything to the newsletter, and that it was really disappointing that people weren't participating, and that people better step up their game or there were going to be no more newsletters. And thankfully there were. And I also, just as a total random aside, I was just really amused by this, that this is how postdocs used to get jobs. So if anyone would like to apply for this position with Steve Roper, I believe he is looking for a postdoc. And I would say Tom Finger is also looking for someone. And Tom, I hope you pay more than $15,000 a year for postdocs. And as a final point, can we bring back this logo? This logo is awesome. I mean, this alligator, that's really cool. You know what? I shouldn't have shown you this. I should have entered this in the logo competition next year and no one would have known. Okay, so anyway, I like to read old stuff. Or at least for me, this is old literature, because I won't tell you how old I was when this book came along. So in a lot of the old books from these symposia, what they would do is after the chapter where someone presented their work, they would actually go and have the question and answer session and actually write down what people said. And so in this book, on page 65, Judy Rodin, who then went on to be the president at Penn, said, "Why is the literature on taste interactions in actual foods and beverage so sparse and unsophisticated?" And Rosemary gave about a 14-point answer. And she started out by saying we could get useful behavioral data on discrimination and perceived intensity from model solutions, but she also said that trying to predict, using model solutions to try and predict real foods was an exercise in futility. And she said that the data that we had was very sparse for many reasons. She outlined 6. There are very few people that were actively working on food. Most industrial researchers weren't publishing their work. It was unusual for sensory analysts or sensory specialists in food-oriented fields to use good psychophysics and for psychophysicists to be well informed about the functional properties of food. I don't think this point is true anymore. I think there's enough of us around that are dually trained in both disciplines that we've at least solved this one. She said that both psychophysicists and sensory analysts are justifiably intimidated by complex stimuli, where a change in one single ingredient can alter multiple sensory attributes simultaneously. She pointed out that reliable human experimentation is slow and labor-intensive, and that there wasn't enough money. So I work in a food science department, And so if you're going to do psychophysics in a food science department, you probably should do it on food if you want to keep your job. And so that often means working with really, really messy stimuli. So here we have Nadia absolutely covered in whatever just exploded all over her. Or we have people cleaning vegetables. Or as Linda was talking about yesterday, working with actual horticultural products. When you pay undergraduates to cut up thousands upon thousands of peaches, and then you're left with giant crates of peaches all over the laboratory for the next month. It's a very delicious problem to have. So when we think about psychophysics, and you think about introductory psychophysics, the first place most people start is with thresholds. So if we start with the idea of a detection threshold, that's the lowest concentration at which we can perceive something. So in terms of a light stimulus, it's the number of photons we would need to activate a photoreceptor. If we're thinking about a chemical stimulus, it's the minimum concentration required to provide a ligand to bind to that receptor. But we can also think about a difference threshold. So a difference threshold is instead defined as the change in energy required for us to notice a difference in sensation. And one classic way to do this is with the method of constant stimuli. The original version of method of constant stimuli only used a single stimulus, but then thanks to signal detection theory, we eventually updated this to be a forced choice task. And so I simply give you two samples, and I say which one is sweeter. And if I do this over and over and over again with one participant who has to do thousands of trials, and it gets quite fatiguing, or I can do it on a group level, what I can do is I can get a psychophysical function like this. So here we have a sample of sucrose, that's our reference, that's the constant in the constant stimuli, and so 10% sucrose. And if I give you 14% sucrose, about 95% of the time you're going to say the 14% is sweeter than the 10%. And we can do this in the other direction, and we can get a very nice curve, and I can eventually figure out the concentration where 50% of people give that concentration, and we get a match. Well, we wanted to know how this is true for wine, because if you're going to work on food, you should work on something fun, right? So this is a view from one of the booths in our lab, and so here, this is how we might evaluate wine. And it turns out that most wine today, regardless of what the wine snobs will tell you, there's a false consensus bias among wine snobs. They all want everyone to pretend that they want really dry wines, but that's not actually what the consumer wants. Sales data shows us that. Market research data from Gallo shows us that. People want sweet wines. So traditionally, the way you made a sweet wine was you stopped the fermentation early. You halted the fermentation before all those microorganisms, all those yeast could then chew up all the sugar and turn it into ethanol. The problem is that's not what the consumer wants today either, because they also want a high alcohol wine, because they want to get their drink on. So what you do if you're a winemaker is you ferment it all the way dry, and then you back sweeten by adding sugar later. So we wanted to know, okay, what's the difference threshold? How much sugar can you add before people can notice? And so we did this with many, many, many hundreds of comparisons using the method of constant stimuli. And what we actually found was that when you have Merlot and you back sweeten the Merlot, and I know those of you that are wine snobs are absolutely cringing at this thought, but if we back sweeten our Merlot, what we find is that if we wanted to match 11% sucrose, we can actually move the sucrose percentage over 3% before people will notice. And we did the same thing with Pinot Grigio, and we found the same thing. So you can actually move the sucrose percentage. This is weight per volume sucrose. So this means if you're a winemaker now and you're worried about back sweetening your wine, you need to add sucrose by the shovelful before people can notice. So let's go back to some Psychophysics 101, because this is a psychophysics award. A Weber ratio we can define as the ratio between the just noticeable difference, which we can think of like the difference threshold, over some stimulus intensity. And so for sucrose and water, if you go back and look at the various values in the literature, you get a Weber ratio of somewhere between 0.08 to 0.13. So let's just say 0.1 to make it easy. So in water, how much do you have to change the sucrose percentage before people can notice? And it turns out you need to move about 1 to 1.5 or 2% sucrose, depending on which Weber ratio you use and where your starting point was. But you can move at about 1%. So then we wanted to know, okay, so what does it look like for wine? And so we calculated it for wine. And for red wine, turned out the Weber ratio was about 0.29. For white wine, it was about 2.8. So we went back to the literature. Surely someone's done this before. We cannot be the first person ever to do this. And we only found one single reference. And the reference we actually found was actually a Pangborn paper that she'd done in collaboration with some Swedish colleagues. And it was published in the second edition of Chemical Senses when it had its original name. For those of you that can't read the slide, what was the original name of Chemical Senses? Chemical Senses and Flavor. So it's appropriate that Flavor won the baseball game today. Okay? And so what's the answer that we got? Lo and behold, the closest thing we could find was orange juice, and that's the Weber ratio for sugar in orange juice. So it tells you that when you're talking about a food matrix that has acids and has Valdos in there, you need to have a much larger amount of sucrose to change before you can even notice it. So this, again, reinforces Pangborn's point that trying to predict what's going on in real foods from simple aqueous solutions is often an exercise in futility. So we heard a lot about detection thresholds from Terry Akery the other day and Thomas Hoffman. And just to show you, these are two odorants that are really important for wine as well. This is methylanthenolate. This is what gives Niagara and Concord its grapey smell. This is 2-AAP, which gives the same native North American grapes, that foxy smell that you get. Ask Terry why it's called foxy. I'm not telling that story in public. But what you see is a very, very small difference in structure changes the detection threshold for this. This is fundamental chemical psychophysics. This is not surprising to anyone. But then again, we wanted to look at what happened when you actually looked at foods or looked at real systems. And so here, this is Demi Perry's master's thesis work. And what she shows here is the blue line is the detection threshold in water, and the orange line is in wine, and the black line is in model wine for methylanthenolate. And we did the same thing for 2-AAP. And what you actually find is over an order of magnitude difference in the detection threshold for these. So moving from, again, a water-based system to a complex system like real wine, you actually have a massively different answer. So this is why I would say, I don't know if Thomas is still here, but I would be really skeptical of using a dose over threshold value from the literature when that dose over threshold value, God knows what matrix it was originally calculated in. Okay, but frankly, people don't really care about detection thresholds most of the time, because when I drink my coffee, I don't think to myself, oh, is this a little bit bitter? No, the coffee is bitter. I can tell it's bitter. We live in a super threshold world. So about 10 years ago, John Prescott and some colleagues invented an absolutely, what I think is brilliant technique, which is a really simple adaptation to a very old school psychophysical idea. They invented a technique called a rejection threshold, which is not instead asking, can you tell it's there, but do you care? So they went and they gave people a compound and they said, which one do you like better? And you do a series of paired comparisons. So we thought this was pretty cool, so we took it and we ran with it. But of course, again, I work in a food science department and I have access to things like giant processing facilities right in my building. And so we made chocolate milk. And when we did our chocolate milk, what we did is we actually segmented people ahead of time and we spiked this chocolate milk with sucrose octaacetate. I'm a horrible, evil person. That was disgusting. But when we did this, what we found was that at some concentration, there was no difference in preference, but at a different concentration, we got universal rejection. I managed to make everyone hate chocolate milk, okay? But what's really fascinating is in between, there's some sort of concentration where, oops, went ahead a slide, I'm all good. So there's some concentration where we actually got some segmentation between the people that, believe it or not, that like dark chocolate when they eat solid chocolate and people that like milk chocolate when they eat solid chocolate that actually predicted a over twofold difference in the concentration at which they objected to bitterness in chocolate milk. So being good food scientists, we want to study matrix effects. So we made chocolate ice cream and we did the same thing and we found the exact same pattern. Then we made solid chocolates. We fed those to people and we got the exact same pattern. So then we decided to look at matrix effects. And what we found is if you ignore the segmentation and just look at the grand means across all the experiments, you find a very nice ordered relationship moving from the fluid chocolate milk to the ice cream to the solid chocolate. So again, the matrix matters. We went back down to our plant and we made some milk. This was not chocolate milk, this was white fluid milk. And so when you take white fluid milk, what you actually do is you split all the cream out, and then you homogenize it, and then you actually standardize the milk where you blend it back together at exactly the ratio that you want. This is done in every dairy around the country because they pay for milk not on the basis on volume, but on the basis of the milk fat percentage. So that's why people that say raw milk is so much creamier, yeah, raw milk is creamier not because it hasn't been pasteurized, but it hasn't been standardized. It's up 4.5% fat. So of course it's more creamy. But anyway, that's an aside. So we went down and we made a bunch of different fluid milk samples. And what we were actually able to show is that when we compared it to people's typical consumption preferences, we actually found that there was a group of people, those blue spheres, those blue circles, those are people that drink whole milk. So they really liked the whole milk. And then there was everyone, and the relationship was kind of flat. And then we looked at the people who drank the skim, and there was really no relationship. But then we thought, well, wait a minute. Lots of people drink skim milk, not because they like it, but because they're worried about health concerns, right? They don't want the calories. So we've said, if you could drink whatever you wanted and you didn't have to care about health, which one would you drink? And so we took the exact same data and we resegmented it. And what we actually found is there's a portion of people that actively dislike fat. So that's the blue open squares, so that with the horizontal line. Those people actually, right here, are actually disliking the milk as it has a higher fat content. And so it's not that everyone that normally drinks skim milk is only making a compromise, but some people don't like it. We don't know what the basis is for that. Could it be biological? Could it be oleogustus? Maybe, I don't know. Somebody needs to do that work. So I'll just throw that out there. So it could be that people are picking up differences in free fatty acids in the milk, and that's why they don't like it. So speaking of free fatty acids and oleogustus, we decided to look at chocolate, because if you're going to look at foods, you want to look at fun things. And so we took stearic acid and we spiked it into solid chocolate, which we then melted and told people it was a chocolate sauce. And so in that chocolate sauce, we essentially found that there was absolutely no relationship between stearic acid and the ability to accept or reject that chocolate. But when we did it with oleic acid, what we instead found was that there was a rejection threshold that we were able to reach. And you're noticing that it says taste and aroma. So we did one of these with the nose clipped. So everyone out there probably thinks, oh, free fatty acids have a smell to them. But it turns out they also have a taste to them. And even when we occlude olfactory input, we can still actually make people hate chocolate by putting free fatty acids into it. And then being the good chemists that we are, we decided to look at linoleic as well, and we found an even lower rejection threshold for linoleic. Okay. But of course, thresholds are not intensity measures, right? Because things have different psychophysical slopes. So here we have 3 different compounds, and what we can actually see is that this compound in red here, methylbenzoate, has the highest threshold of the bunch, but it actually has the steepest psychophysical function as well. So you also need to keep this in mind when you're thinking about, well, how intense is that compound? Just knowing the threshold really won't tell you that much. So this brings us to the 1950s. S.S. Stevens got into an argument. This is actually where magnitude estimation came from. When I actually found this paper, I was absolutely floored. So Stevens was actually arguing with someone, and the colleague, who he never names, said, you seem to think people could assign a number to the intensity, because of course, remember up until this point, people had been using all forced methods, indirect scaling methods. And Stevens said, yeah, that's an interesting idea, let's try it. Now, what's kind of ironic is, if the psychologists had bothered to read the food literature, they would have actually found that the food people were already doing this. So here's a paper from Howard Schutz that was done with Francis Pilgrim by the US Army, and I've underlined a portion here that says, many studies have shown people are quite capable of expressing their judgments of attributes or qualities directly on the basis of an underlying subjective continuum. And so they went and they figured things like dose-response curves out for sweetness. This is much faster than using the method of constant stimuli to try and figure out these relationships. And so we did this looking at a whole bunch of different sweeteners a few years ago. So we looked at sucrose, aspartame, Rabe, ACE-K, and sucralose. And what you see is that all the non-nutritive sweeteners are left-shifted here because they are more potent. But what you also see is that all those sweeteners never actually get as sweet as sucrose. So this is why when the food industry calls these high-intensity sweeteners, they're fooling themselves. They are not more intense. You use less of them because they are more potent, but they're not more intense. And then we looked at agave nectar, and we looked at maple syrup as well. So for those of you that use the agave nectar when you go to Starbucks, it is actually sweeter than sucrose. So this is, again, an example of when you actually start thinking about real foods, you can start to see some patterns that you would completely neglect if you only looked at things in water. So I'm quickly running out of time here, but I wanted to talk quickly about mixture suppression. So mixture suppression is a phenomenon many of us are aware of. Here's data from 1979, where Harry Lawless elegantly showed that mixture suppression is a central phenomenon. It had previously been documented in the literature, but through a series of experiments, Harry showed that it was a central phenomenon. And the way he did that was he gave people sugar by itself, and that's how sweet it is. He gave people PTC by itself, and that's how bitter it is. And when you mix them together, you get mutual suppression of sweet by bitter. Now, I don't have to explain to this audience that some people can taste PTC and other people can't. So lo and behold, when you mix it for people that are PTC non-tasters, these are the results you get. So there's no mixture suppression. And it's very obvious to us in 2016 how this is going on. But in 1979, we had no idea what the receptors were. So this elegantly shows that it's not a physical phenomena at the periphery. It's not some sort of receptor blockage coming from the PTC. It's actually a phenomena that must be happening higher up. And he also confirmed that by showing it with split tongue studies as well. Okay. And so, I don't know, are Gary and Paul in the room? I can't see through that light. But so they followed up on this later and have a great Nature paper where they show that sucrose and urea, we get the same sort of mixture suppression. And when you mix them, you depress their responses. But it turns out if you add a little salt, you get release from mixture suppression because now you've blocked the bitter input at the periphery, and so you never get that central suppression. Now, this is a phenomena that chefs and many of the public have known for decades, right? This is why people salt grapefruit or salt watermelon. You sprinkle a little bit of salt on because then you block the bitterness, which then causes the sweetness to rebound. And so we actually showed that in low-sodium cheddar cheese. So here, if you look at, obviously, the low-sodium cheddar cheese is going to be less salty than the regular sodium cheddar cheese. That's not rocket science. But what we also found is that when you take the sodium out of the cheese also gets more bitter. So now if the cheese is less salty and it's more bitter, what do you think is going to happen to the liking? This isn't real complicated. People aren't going to like it, okay? And this brings us back to what Pangborn warned us, that you change a single ingredient, you pull the sodium out, and you've now altered multiple sensory attributes. So again, this is why working in model systems can be dangerous if you're trying to understand behaviors related to real food. And this also has really important implications for the food industry, because it says instead of looking at a salt potentiator, when you pull that sodium out to keep it equally salty, maybe that salt is really having a functional role of blocking the bitterness. So instead, what you should be doing is adding a bitter blocker along when you take the salt out, so that then what saltiness is there comes through. I'm going to skip this slide in the interest of time, other than to just say that saltier isn't always better. When you have potato chips, saltier is better. When you have pretzels, saltier is better. When you have soy sauce, saltier is not better. So this is, again, showing us that real foods don't always generalize from simple mixtures. So what are my take-home messages? Psychophysics is dead, but it survives in places like food science departments. Chris Simons and I have had this discussion at length, that I don't know of any psychology programs left in the country that still teach psychophysics. So you have to go and give the Barry Jacobs Award to a food guy like me. The matrix matters a lot. It's hugely important for when you're trying to understand these things, of knowing, the partition coefficients, if you're working in wine, what's the volatility in water versus water with ethanol, etc. Working with food is really hard because of all the stimulus control stuff. It's incredibly slow because you have to make all these samples. But it's also really important. Oops. So I will wrap up, and I will thank my team. These are all the master's students whose work I presented. Some of you remember Demi from last year when she probably ran past you in the 5K, which apparently we don't have anymore for, hopefully no one went to the hospital from the softball game. And I would especially like to say, please check out Corey Running's work if you haven't already. And here she is for her going away gift with a 10-pound bar of chocolate, because that's apparently a standard thing to give people when you work in a food science department. And then finally, I would like to plug our new book on chemesthesis. And many of the people in this room are authors of the chapters in here. So please check out this book and buy a copy. So with that, thank you very much.